Okay, let's dive into this. Welcome to The Explainer. Today, we're taking on a concept that honestly sounds like pure science fiction, but it's actually the foundational reality of our entire universe, quantum superposition. We are going to move way past the pop culture hype, tracing the timeline all the way from the mind-bending paradox of Schrödinger's cat up to the absolute game-changing engineering breakthroughs happening right now in 2026. By the end of this, we're going to truly understand what superposition is, how it functions, and why it is absolutely the key to our next major technological leap.
So, let's start with a classic. Is Schrödinger's cat alive or dead? You've probably heard of this one, right? It's easily the most famous paradox in all of physics, and it brilliantly highlights the totally bizarre scenario that unfolds when we try to take the strange, probabilistic rules of the microscopic quantum world and apply them directly to everyday macroscopic objects. Here is our roadmap for how we're going to unpack this together step by step. Number 1, the famous quantum cat. 2, how superposition actually works. 3, the math behind the magic. 4, the problem of decoherence. And 5, powering quantum technologies.
Let's kick things off with Section 1, the famous quantum cat.
You know, there's a massive gap between pop culture and actual physics when it comes to this poor feline. The pop culture myth tells us that the cat is literally some kind of undead zombie, existing as both alive and dead simultaneously inside a sealed box, until we open it. But here's the truth, and it's actually kind of funny. Erwin Schrödinger didn't believe in zombie cats. Not at all. He designed this thought experiment back in 1935 as a ridicuo ad absurdum. He was basically critiquing Niels Bohr's quantum interpretations. Schrödinger wanted to highlight the sheer absurdity of standard quantum theory when you try to scale it up to macroscopic objects. Basically, he was trying to prove the theory was incomplete if it suggested a cat could be simultaneously dead and alive.
Section 2, how superposition actually works. Now, what's really interesting here is how we pivot from theoretical cats to physical reality. To do that, we actually have to trace the concept all the way back to Thomas Young's 1801 double-slit experiment.
So, what is quantum superposition? It's defined as a single quantum system existing in a combination of all possible states simultaneously, each with its own probability amplitude, until it's measured. Now, it's absolutely vital to distinguish this from regular classical uncertainty. Think about it like this. If I hide a coin under my hand, it's already heads or tails. I just personally don't know which one it is yet. But in quantum superposition, a particle does not have a single definite state. It is genuinely in all its states together until the act of observation literally forces an outcome.
So, the crucial point is how this applies directly to information. There's a massive difference between classical bits and qubits. Classical bits, the ones running your phone and laptop right now, are tiny electrical switches that are strictly either 0 or 1, kind of like a coin sitting perfectly flat on a table. But qubits, or quantum bits, can exist as 0, 1, or a linear combination of both states simultaneously. Imagine a coin spinning in the air. This fundamental difference is exactly what allows a qubit to hold and process vastly more information than a standard classical bit.
Moving on to Section 3, the math behind the magic. Now, I know math can be intimidating, but we're going to ground this abstract concept in actual mathematics, and I promise you it is elegant, precise, and completely accessible. No physics degree required.
Okay, let's break down this ket notation equation. It's much simpler than it looks. That Greek letter psi on the left, that simply represents the wave function of our system. It equals alpha times the 0 state plus beta times the 1 state. Now, alpha and beta are just complex numbers called probability amplitudes. According to a principle called the Born rule, if you square the magnitude of those amplitudes, you get the actual real-world probability of measuring the qubit as a 0 or a 1. And as you'd expect, those squared probabilities have to add up to exactly 1, or 100%.
And this brilliantly illustrates exactly what we're talking about. We can map that exact math visually onto what's called a Bloch sphere. It shows how a qubit state tilts between 0 at the North Pole and 1 at the South Pole. That vector pointing out to psi, that is our superposition. The angle of that tilt visually represents those measurement probabilities we just talked about. It's just a really beautiful, concrete way to picture how a quantum state exists in three-dimensional space before it collapses upon measurement.
Now let's look at the sheer mind-blowing power of exponential scaling. Because qubits can exist in these simultaneous states, a system of n qubits holds 2 to the power of n states simultaneously. 3 qubits give you 8 states, 10 qubits give you 1024. But here's the crazy part. If you can perfectly string together just 300 qubits, that system exists in 2 to the 300th power simultaneous states. To put that into perspective, that is literally more states than there are atoms in the entire observable universe. No way, right? But it's true. This vast parallel solution space is exactly why quantum computing holds such revolutionary potential. Which brings us to Section 4, the problem of decoherence. This naturally sets up the physical limitations of these systems and the massive engineering challenges of actually building them. So you might be wondering, if this exponential scaling is so incredibly powerful, why on earth don't we see superposition in our everyday lives? Why isn't your coffee mug existing in multiple states right now? It really sparks our curiosity about the boundary between that fragile, microscopic quantum world and our robust classical reality. Well, the culprit is a little something called decoherence. You see, any interaction with the environment basically acts as a measurement that completely destroys that delicate superposition. We're talking thermal radiation, a bouncing air molecule, stray photons, literally any environmental interaction. The moment the quantum system interacts with these uncontrolled external forces, the superposition collapses almost instantly, forcing the system right back into a single classical state.
And we can connect the physics of decoherence directly to modern engineering. Because of thermal noise, quantum computers built with superconducting qubits have to operate at roughly 15 millikelvin. That is colder than deep space. Even the slightest, tiniest hint of warmth causes the qubits to interact with their environment, which ruins the quantum calculations before they can even finish. It is just a monumental engineering hurdle.
Finally, Section 5, Powering Quantum Technologies. Let's move to and see how this builds, exploring how scientists are harnessing these microscopic phenomena to drive macroscopic technological breakthroughs today. Because superposition isn't just theory anymore, it's actively being applied across some really diverse fields. In quantum computing, it allows processors to explore vastly larger solution spaces in parallel. That's a huge deal for complex optimization, stuff like global logistics or portfolio management, and for simulating molecules for drug discovery. But it's not just happening inside a supercooled fridge. In quantum biology, evidence suggests superposition is actively occurring in nature. It facilitates highly efficient energy transfer during photosynthesis. The energy essentially exists in multiple states simultaneously to naturally find the single most efficient path to a plant's reaction center. How cool is that? Let's chart this fascinating journey from abstract theory to our current reality. We started way back in 1801 with Thomas Young's double-slit experiment. By 1935, Schrödinger was proposing his famous cat thought experiment. But look at where we are in 2026. This year alone, Google's Willow processor proved that logical error rates actually decrease as systems scale. And simultaneously, atom computing created 24 logical qubits using neutral atoms. These 2026 breakthroughs are a huge deal because they mean quantum error correction has finally moved from being just a cool physics experiment into a viable, scalable engineering pipeline. But we have to talk about why this matters on a security level. As this hardware matures, it brings a very real post-quantum threat. The mathematical algorithms that secure our digital lives right now, like standard RSA encryption, they can be broken by large-scale quantum computers. And adversaries are already executing a harvest now, decrypt later strategy. They're gathering your encrypted data today, just sitting on it, so they can decrypt it once fault-tolerant quantum hardware is fully available. It is an absolutely urgent cybersecurity priority for all of us. So, we've seen the immense universe-scale power of the quantum leap and the massive engineering efforts required to control it. But I want to leave you with this final thought. As quantum systems scale up and error rates continue to drop, will our classical reality survive the superposition? The future of physics is literally being engineered right now. Keep exploring.